We are now live. Oh, this is going to be such a pain. As
I'm sorry. Some of us have to do this all the time. You will be completely fine.
I, I live my life in a way that I never have to manually switch the camera unless I want to. But here we are. You've driven us to this. So,
Well, you can just leave it on me the whole time.
sure, that's fine. That works for me. And look at that background. That is so great.
I'm currently in San Francisco. I'm staying in a hotel on the 18th floor down off Powell Street. It's a fabulous view, and I really wish I could record like every episode ever from this chair, because it's also a very comfortable chair that is perfectly shaped to put my laptop on and get good camera angle.
So we know that you're going to need to, in the future, get some really fancy apartment in San Francisco, which we all would like, I think.
I don't think as an academic I'll ever be able to afford that.
Oh. Okay, cool. So I'm waiting for a viewer. Oh, there's two viewers, so it looks like there's somebody there. I'm going to say hi to some people. We got Matt Woods. We got Steve Chisnell, Dusty Reichwin, Richard Clark, and Giselle Sabarin. Now, I don't know whether if you're all still watching, because we had to do a time shift because Pamela was on a train.
Yeah, it was one of those days.
Cool. Okay, so we're gonna take half an hour-ish to do this episode, and then we'll stick around. Although I think you're probably fried from all of your travel, and yeah.
You probably want dinner.
Yeah, exactly. I want some dinner, so we'll probably keep this pretty quick. But which is too bad because this is like literally one of my favorite conversations. And just to warn you, we are gonna go so into Crazyland today that you're gonna have to rein me in, Pamela.
This is
way
my
out there.
Christmas gift to you, is I knew when I picked this, you would greatly enjoy this and go into Crazyland, and you would enjoy every moment, and I might want to kill you, but it's my Christmas gift to you, so I won't.
Well, thank you so much. Okay, great. Well, let's begin, and I apologize. I'm going to be manually switching the camera here, so Matt says, Fraser, you're going to have to up your game in background department. Oh yes, I need a better stuff in the backgrounds. No problem. We're working on it. We're getting there. I got those great posters. I've got the most importantly the 2 Parsec awards. I mentioned the 2 Parsec awards.
I have 1 Parsec and 1 Communicators award.
All right, I don't have any of those. How do I get one of those? I want to.
I'm not
get
telling.
one of my. Okay, fine. All right. Okay, well, let's do this thing. Let me know when you're ready.
I lost my Audacity window. How did I lose a window? Hold on. Sorry. So answer questions while I try and figure out how I lost Audacity.
Okay, sure. Dusty Reichman says, "Yay! I can watch live for change. Yay, Dusty! Yay!
Yay!"
Giselle says, "Hi, everyone from Montreal, Canada, which is great. More Canadians watching the show. Made by Canadians for Canadians." Matt Wood says, "Hey, Perth from sunny Perth, Australia, for all the Northern Hemisphere people suffering through winter. This is where I'm watching the Hangout from." And then he posts some link to, I'm sure, some ridiculous, beautiful, sunny beach in Perth. Good, Matt. Good on you. We had really cold weather here last night. In the negatives, anyway. Probably minus 5, minus 6. It was pretty cold.
Weather in America right now is just screwed up. I saw an infographics today that was showing that like Arizona is one of the coldest places in the U.S. right now.
Well, I don't know if you remember last year. Was it last year when you had that huge winter storm that came really deep down?
Yeah.
And Susie, one of our producer in Atlanta. Yeah, had minus 10 Celsius and like freezing snow, rain, and it was just an absolute disaster. It was terrible, like way colder than we ever get here in Canada. So yeah, no, terrible. Oh right, Matt says, oh yeah, I see. Pamela has a city behind her, so I lose. That's true. Yeah, I see why I have to up my background game. Paul Nash says, hi from Philly area. Pump. This is my first live viewing. Well, welcome, Paul. For your
Awesome.
first time, it's great to have you. Long time listener, first time viewer, first
Cool.
time in the sausage factory. Is that what? So, all right. Are you ready now?
I am. It turned out I forgot that I'd redone this computer and it didn't have the security setting to allow Audacity to open.
Just say when.
I'm ready. Go ahead.
Tell me
Pressing
when you've
record.
pressed record. Okay.
I've pressed record. It is recording. The audio levels don't suck. I'm sorry,
Testing,
Preston.
testing.
This is a different mic.
I'm not sorry, Preston. You're gonna have to just edit your magic. Here we go. Astronomy Cast, episode 397. Why is there something and not nothing? Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos. We help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today. With me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
Great. As we are speaking right now, it is the height of the Geminid meteor shower. We had beautiful clear skies last night, and a couple of friends got a chance to see some. As soon as this show is over, I am gonna, because we're recording in the evening unusually, I'm gonna go out and try and catch them on Monday. Although it's also bitterly cold here in Canada, so I'm gonna see how long I can last outside as I look for Geminids. But the Geminids are at their greatest, at their peak, which people don't realize now. The Geminids are really like one of the biggest meteor showers that we can get. So
I was actually born during the Geminid meteors, and somehow that has explained so many different things.
yeah, your birthday was yesterday?
Saturday.
Saturday, right? Okay, yeah. Okay, well, let's get on with the show. So one of the biggest, most basic questions you can ask is, why is there something and not nothing? And the reality is that we don't know the answer. We might never know the answer. But let's probe to the edge of what we can explain and what ideas cosmologists have proposed to explain how we all got here. All right, Pamela. So this is a special holiday gift to me that you're willing to entertain my wild flights of fancy and talk about a topic that normally you wouldn't touch with a 10-foot pole. So
Exactly.
I deeply appreciate you playing ball. and this is like my favorite question to ask to stump cosmologists and stump scientists, because I mean, obviously the answer is we don't know.
Yeah.
But what I love is how they explain we don't know. So before we kind of get into this, let's get right to the limit and sort of, let's talk about the Big Bang theory itself and where it ends. If that
Okay.
makes sense.
Yes. So the Big Bang Theory basically explains that our entire universe originated 13.8 billion years ago, and it arose out of a single point. Now, as the theories go currently, this single point underwent rapid inflation, and within the first 3 minutes, pretty much everything that we have in the universe went from a point of pure energy where all the forces were tangled together to the forces breaking apart to particles falling out of the energy to a burst of nuclear synthesis that got us helium, a touch of lithium, a bit of beryllium, and of course we had hydrogen. And then the universe basically expanded and cooled and expanded and cooled and expanded and cooled until somewhere between 300 and 400,000 years after the Big Bang, at which point the universe had expanded and cooled enough that atoms were finally able to form out of this melee of colliding particles. And when this happened, the electrons glommed on to all of the completely ionized nuclei that were flying about, and we ended up with a neutral universe that was dense and dark, and the release of the cosmic microwave background radiation.
And there are multiple lines of evidence. We've done a whole show about this. I've done a video about this. There are multiple lines of evidence, each of which confirms that the universe is currently expanding away from it, that everything in the universe is expanding away from each other, that if you run the clock backward, you get to that 13.8 billion years that you mentioned. So the Big Bang really wonderfully explains sort of that everything is moving away from each other, that if it was once a singular point. That's all great. But it falls apart, obviously, or it doesn't fall apart isn't the right term, right? Is that it fails to explain what set off the whole process in the first place.
Right. So we're in a situation where, for the best of our understanding, we can say that everything went down to a point. Now, the question that we get left with was this part of a wave function collapse where the point wasn't a point that then stopped at the point, but rather was just sort of passing through as things went sprawling or as wave functions changed? We run into problems of we observationally can't see anything from before the formation of the cosmic microwave background, so is it even valid to discuss what came before the Big Bang when we can't even see what happened before the CMB? And then you run into problems like, how do you try and understand all of this within the context of the arrow of time, this fact that there's so many things in our universe that require time to be a constant step in a single direction. For instance, while there's a lot of movies of pool balls colliding that if you ran them forward or backwards you'd never be able to tell the difference, there are a lot of situations that the science only runs in one direction. For instance, if you throw a water balloon at someone, that's a video you can tell instantly whether or not you're watching it in reverse, because once that balloon pops, that water and plastic isn't spontaneously going to recombine to recreate that water balloon. So how do we explain a universe that appears to always be marching in one direction? It's very uncomfortable to think about, did it come out of an infinite past and go into an infinite future in this constant line? It seems like it should somehow circle back on itself, but you can't do that if time only marches in one direction. And so people are trying to figure out, how do we uncouple all of these different problems? And then there's the most fundamental problem of all, which is once you're within the smallest fraction of a second, once you're within Planck time, suddenly you have to be able to unify general relativity and quantum mechanics in order to have a coherent conversation. And those two things don't work and play well with one another.
So, I mean, our instinct is to sort of imagine, as you said, time marching forward, event after event, unfolding one after the other.
Right.
But with the universe, as we currently understand it, not only was the whole universe sort of down into this initial singularity, but time itself began with the beginning of the expansion of the universe. And so, it's bordering a nonsense question to ask what came before time, right? What is more north than north
right.
is one of the problems. But I think, you've got at least a little bit of a stepping stone there, right? Which is what you mentioned, is that we can't even still explain how gravity and the sort of grand unified,
there is no grand unified theory.
Right. There is no grand unified theory that includes gravity, and so it's like that the last rung on the ladder to that singularity still hasn't yet been figured out. So there's still hope to push the boundary at least a little bit more forward. Right.
And it's a hope that some of us are starting to feel less and less sure is actually going to hold out. And it's possible that either gravity simply doesn't have a string theory or a particle physics or a standard model way of being discussed that makes sense within our current paradigm, and it may be generations before someone who's able to create that fundamentally new paradigm comes along. So there's that challenge of we need to give birth to a new paradigm changer. Then there's the problem of, are we getting stuck by our own closed-mindedness? A lot of people are constantly going down the same road of string theory, which is admittedly the only direction where new ideas have been generated for a while. But there's no evidence for string theory whatsoever. So the big theory that people are trying to figure out if they can work on is the idea that the Big Bang comes out of the collision of string theory membranes, or just brains is what they usually call them. And the math actually works out with this theory that it's sort of like three-dimensional sheets of paper floating through a many-dimensional space, sort of like a two-dimensional sheet of paper blowing in the wind in our three-dimensional space. And when two of these brains collide, they end up generating a stable new space in which we could maybe possibly exist, but we don't know. And so that's one theory that's being worked on.
Right, and if I sort of understand that, you know, when you get these potential collisions between these membranes, which is probably not anything like what they actually are, if this is correct, you know, we imagine these sort of, you know, membranes because our puny meat brains can only imagine this kind of thing.
Right.
But that you sort of get the you know, we actually talked about this just a couple of episodes, you know, the frustrating fact for most physicists that a lot of the pieces of the universe are these constants. This is how strong gravity is. This is how strong alpha is. This is how strong the weak force is. And that all of those sort of fell out as, you know, they got hard-coded into the universe when this interaction happened. So that's sort of one implication from string theory, but that's just, you know, one possible idea, right?
That tangles it slightly. So we're looking at a couple of different things. So the theory that I'm talking about is one that came from Paul Steinhardt and Neil Turek, and I started this work back in 1999 at a cosmology forum where they were both having this moment of, how do we work ourselves out of this hole that the Big Bang has dug us into with the beginning of the universe? And with the collision of brains, what you actually can end up with is an oscillating universe system. So you have this multiverse, and with the multiverse you can have different physical parameters tumbling out of different colliding brains and out of different oscillations. But side by side with that, you also have Andre Lin's idea of infinite inflations, where you have inflation once it gets going. You might end up with parts of it that just keep bubbling off, and each of these different bubbling bits and pieces is its own universe with its own physical constant. So there's multiple ways to get to multiverses.
And so what you're saying with that other sort of multiple inflations then is that there's some other universe, and then I guess things inflated to the point that it's almost like it branched off and began its own timeline with its own constants.
Exactly.
That we then experience in. So time began for us in this universe, but maybe there was time previous, you know, in whatever was the universe that we branched out of.
Or even a more interesting idea, and this is one that's been getting worked on by Sean Carroll a lot, is that in this bubbling froth of bubbles, perhaps in our universe time is going in one direction, and in another universe time is going in another direction. And because there's no particular favored direction for time, not that it can go sideways, but it sometimes feels like it goes sideways. But anyways, since you can have some universes with time going forwards and some with time going backwards, you get closer to the North Pole is the farthest north you can go, but you can still keep walking. And so you don't have that infinite beginning problem.
One of the really interesting calculations that I'd seen Sean Carroll had done was, there's this idea of sort of quantum fluctuations that you can, the air in this room is most likely, according, the probability is that the air in this room is going to remain in this room, but there's a really super remote chance that all the air could suddenly rush up to one tiny little corner of the room and I could suffocate. Yeah. But most likely that's not going to happen. But then you sort of take that idea of quantum mechanics further, and you can imagine sort of virtual particles appearing out of nowhere, and you can sort of take that to this idea that you could have, they talk about Boltzmann brains, this idea that, that eventually if you run the numbers long enough, that actual particles and eventually even completely conscious minds could appear, which then would collapse other waveforms. That's sort of, but he even ran the numbers all the way to what it would take for an entirely new Big Bang to form. And the fact is that if the universe the universe might be infinite in size. Mm-hmm. And so if it is infinite in size, then if you run the numbers long enough, this is going to happen. And not only that, it's going to happen an infinite number of times. That, random luck is going to organize all of the particles into another Big Bang. But for sure, or it definitely appears that the universe is going to be infinite in time. And so if we just wait long enough, I forget what it was, like 10 to the power of 50 to the power of 50 to the power of 50 or something just ridiculous, a number that is so big it's just beyond all comprehension. Yeah. That you'll get another Big Bang, that all of the particles of the universe will form themselves into a Big Bang and then begin the expansion from there, that they will all collapse down into this momentary point. And so, with fairly reasonable theories that physicists have seen, this idea of quantum mechanics, particles, virtual particles popping in and out of existence, that you could just do the math to come up with a situation where you get all that, which is kind of amazing.
And one of the cool phrases that I ran across while prepping for this show was, all you need to generate a universe is an empty vacuum and a shard of dark energy. And the idea is that wherever you have vacuum and energy, particles are going to spontaneously come into existence. And more to the point, bubbles of universe are going to spontaneously come into existence. And each of those bubbles, most of them will just burst instantly like soap bubbles. But occasionally you get just the right combination that they grow and grow and grow into something stable that is capable of, rather than bursting, well, supporting entire civilizations.
And yet, the question that you have to ask yourself is, where did that come from, right? That how could you get an empty vacuum and a sliver of dark energy, right? That one thing is a question that has to come from somewhere. So one really interesting book or lecture that I've seen, I haven't read his book yet. This is Lawrence Krauss. He does this great calculation, and he calls his book A Universe from Nothing. And the gist is that if you add up all of the positives and all of the negatives of the universe, right? So if you add up all of the matter, and via E equals mc squared, and you balance that against the dark energy, you balance that against the dark matter, and you balance that against the potential gravity, right? The potential energy from the gravity, the mutual gravity of all those objects, you write this great big accounting of it, and you total it up at the bottom, you get zero. That all the positives in the universe and all the negatives in the universe in the end balance out to zero, which is, the only reasonable answer you could get. Anything else would be quite baffling if you ended up with a little bit more positive than negative in the universe, or a little bit more negative than positive in the universe. But the fact that it actually all balances out to zero is very reassuring, right?
So I have to admit, I didn't even know that book existed. But what I found, which was actually a really excellent read, is Stephen Hawking's on his website, which is hawking.org.uk, has a lecture that he gave on the origin of the universe, and it goes through and it talks about a lot of the stumbles that we've made, a lot of the attempts that people have gone down in terms of trying to understand. And he's the one who I ruthlessly stole the analogy of you can go all the way north, but you can still keep walking, which is where you start to get into a different version of circular time. So I'd strongly recommend going and checking out Hawking's lecture. It's also kind of neat to read because he wrote it to be read by a speech synthesizer. So there's some really funky really funky punctuation in there that's there just to make sure his speech synthesizer sounds rational.
Right. So, what kinds of evidence, as a physicist, as an astronomer, you're always looking for evidence. So what are some kinds of evidence that maybe that cosmologists and stuff are looking for that would try to give some kind of indication about which direction it is? What would be very intriguing?
Well, so as always, people are constantly searching the cosmic microwave background, because that is where all evidence of all cosmological everything at the end of the day needs to appear. And people have been looking for small symmetries. They've been looking for echoes where things are the same in two directions. They've been looking for all manner of statistical fluctuations or lack of fluctuations that will support each of these different theories. Now, at the end of the day, so far, the cosmic microwave background has remained mute on the matter. And we keep hoping the next instrument, the next instrument, the next instrument. So from COBE to WMAP, now to Planck, we keep probing. And
can you explain that a little more deeply? Like you said, an echo. What would that look like?
So for instance, if we live in a somewhat small, finite universe, you will literally be able to see the same light coming from two different directions as the light goes around essentially that four-dimensional hypertoroid that is quite possibly our universe. And so as the light loops around from one point to our point, it's coming at us from two sides.
Right, okay, so it would be like living in a mirror box, and you would look to the left and you see your reflection of what's on the right, and so you know that tells you a little bit about the scale of the universe.
Yeah.
Potentially, maybe what could be influencing it from the outside, if there even such a concept, right?
So we also do look for particular hints that might lead us to say this is where our universe is colliding with another one. This is where we are seeing echoes from different brains. There is a particularly cold spot in the cosmic microwave background that people have been baffled by, and periodically cosmologists pop up with theories of how it might be explained by the influence of a different universe outside of our own, but then another cosmologist always comes along and goes, thump, no. So that is still a debate that isn't solved.
What about gravity? I mean, would one of the ideas I know is that gravity is weaker than the other forces, and this is one of the potentially the implications from some of the theories on this, and that maybe that's somehow leaking from other universes or from whatever, right? And so,
or other dimensions is usually what people talk about. Is since our universe is 3 observable dimensions plus time. And with string theory and pretty much all theories trying to explain the aspects of different particles, you end up having to invoke additional dimensions, the number of additional dimensions, depending on which particular theory. I haven't for a while seen a reputable theory that had less than 11 dimensions. So they're getting up there in number, and gravity, it's thought, might be part of those other dimensions where it's stronger. And I would like to mention, trying to understand all of these different things is part of what leads us to such weird notation like we talked about last week. I got an email from one of my faculty at the University of Texas, Bill Jeffries, who pointed out that one of the reasons that we use the term spin, even though you can't look at an electron and say that sucker is spinning in one direction or another. That not valid thinking. Do not associate the idea of spin with it's spinning like a top. But the reason we use it is the mathematics that get used to explain how particles with different spins interact and work and function. It all requires us to take into account equations that look and act just like angular momentum. So there's lots of stuff going on, and lots of people are trying to figure out how all of this ties together with a multidimensional theory.
And then I guess the other question is that maybe there could be some kind of echo. I mean, we talked about the cosmic microwave background radiation, but maybe there's some kind of echo in the actual vacuum of space itself. The actual structure of space-time could somehow point us towards what might have come before.
And we have been able to start determining certain characteristics about what happened prior to the formation of the cosmic microwave background by looking at what are called the sound waves in the cosmic microwave background. If you look at the statistical fluctuations with the hot spots and the cold spots and how many there are of this size and how many there are of that size, you get this structure of there's this many in this band, this many in this band, and those
I have
things...
to let a dog out. Apologize.
Okay.
Give me 1 second.
Okay. Sorry, Preston. Pausing for dog. I will go back to trying to remember that sentence coherently. Meanwhile, everyone out there, we're really sorry that today's episode didn't get out in time. Preston's Astronomy Cast laptop bit the dust. We've been trying to nurse it along until the next big MacBook release, and it decided it needed to die early. No. So, yeah, we're sorry.
Please continue.
Okay, so as we're trying to figure out how to explain within the context of particle physics all of these different aspects that we can see and measure of particles. We don't see them spinning actually, but we see something that is what induces the Pauli exclusion principle. And that something acts like angular momentum. We see magnetic moments. We see all of these different attributes. Color is, again, we just made that one up. But we see all these different attributes. And people are trying to explain them using multidimensional theories. And in trying to understand our universe with 3 observable direct dimensions plus time, we need to try and understand all of these things that are outside of our observable universe in a lot of ways. And it gets challenging, and multiverses, where you can simply say there is a universe in which everything is possible, just somehow alleviates all of that pain, because what we may not be able to explain except as fine-tuning or something precisely made in just the right way suddenly just becomes, oh, the universe rolled Yahtzee, and a different universe didn't roll Yahtzee.
Of course, you know, if the universe didn't roll the Yahtzee, we wouldn't be here to observe the dice. So, one of the other things that you've mentioned this a little bit, and I think we should probably do a whole episode on this at some point, is this sort of unsettling idea that the universe is one collapse away, one sort of energy drop away from total collapse, and maybe that is the way the universe ends, and then perhaps the way the next one begins, right?
It's the whole idea that nothing likes to stay in an excited state, and we know that our universe isn't in essentially a ground state energy. We are essentially in an excited state. So what happens when the universe decides it wants to, well, become less enthusiastic about existence and drops down to a lower energy, and we go poof?
Right. Yeah, I think we're going to do a whole episode of that at some point.
Okay.
Yeah, which will be great. But I think we're sort of reached the end of this, so that's it. Thank you so much, Pamela, for entertaining me and allowing me to throw this topic on the slate. And yet we tried to keep it in the science. You know, for the person who, I want to sort of give people the sort of one final piece of ammunition, which is, you know, when a person says, well, the Big Bang can't explain where it all came from, therefore Big Bang is stupid, how do you respond to them on that?
I say we can't always understand everything, and this is why we do science. And there's lots of things that it's just going to take time to understand. And this is why we keep looking and keep looking up and keep doing the maths. And the theories that we have right now, the basic Big Bang theory, it explains so many observables that have no other explanation. So we're just one step away, or maybe a few hundred, to study science.
Yeah, and the mystery is worth it. So let's keep looking.
And one final note, we are not going to be back before Christmas because I'm going to be on an airplane back from a business trip next Monday. But I'm going to remind you now, we have shirts like the one I'm wearing right now that says Astronomy Cast on it. These are available at astrogear.spreadshirt.com. And when you support that, you help us do things like replace Preston's broken laptop. So help us replace Preston's broken laptop so no more shows come out late.
All right. Well, thanks, everyone. And thanks, Pamela.
My pleasure.
All right. Stop.
Yep.
Save.
Yep.
Export.
Yep.
Done.
I think Audacity knows that I hate it.
It has revealed that to me a couple of times. It says, Fraser, Pamela doesn't like me very much. All right, let's see what we got here.
Okay.
Paul Nash says, everything from nothing never sat right with me, but if the Big Bang was merely a crossing of all matter, I find that more easily digested. Excellent. Whatever helps you come to grips emotionally with the existential concept that we are existing in this insanely bizarre universe. So,
yes.
Yeah.
It is indeed, if you think too hard about it, something that will cause an existential crisis.
Yeah. Michael Jobin says, what is the lifespan of photons, and is the universe way bigger than the life of a photon?
Photons, as far as a photon is concerned, they exist for like infinitesimal lack of time. They're traveling at the speed of light. Time doesn't exist for a photon.
So this, I mean, we're gonna blow people's minds here in a second here. So as you said, when a photon moves at the speed of light,
yeah.
Therefore, from the perspective of a photon, it doesn't
no time.
experience any time. When it is created and when it is absorbed by whatever it bonks into, that is zero time for it. It is
yes.
both created and absorbed. And so you can imagine literally for a photon, it will experience, especially one that doesn't get absorbed by anything, it will experience the beginning and the end of the universe happened for it simultaneously.
Yes.
And even if the universe lasts forever, it will experience no time. But a photon doesn't decay in the way that an electron may or may not decay, the way a proton may or may not decay, the way we know that neutrons decay. Photons don't decay ever.
Invalid thing to think about because you need time to decay.
Boom. So just walk away with that thought reverberating around your brain. Jeremy Novak asks, doesn't inflation and accelerating expansion break the law of the conservation of energy?
With huh?
Well, just this. I mean, this idea of acceleration, right? This idea of dark energy, that more energy is somehow flowing into the universe and accelerating the expansion of the universe, but energy can't be created or destroyed. So does that violate conservation of energy?
So dark energy, when we use the word energy, it's not energy you can use for anything. So yes, it seems to violate everything, but it doesn't fit into the equation. So we don't know what closed system the dark energy belongs to. One of the most disturbing things about dark energy is, as near as we can observationally tell, every cubic meter of universe contains the same amount of dark energy. And this has always been true, even when the universe was smaller. So while it's invalid to say the universe is expanding into something, if you could say that, which you can't, so this is a crazy statement, the universe is embedded within something that has this constant dark energy. So the dark energy kind of belongs to a different closed system. It hurts.
Right. Yeah, but I mean, it's almost like whether or not it violates the conservation of energy depends on whether you actually know what it is, and whether it's energy, as you said, or whether it is just the size of space-time is expanding, and we don't even know what that is. So, John Schoening asks, do virtual particles physically exist, or are they merely mathematical artifacts used to calculate the interactions of fields? They really exist, right? Virtual particles, the pair, antipair, popping open, that's a real thing.
Yeah, this is why black holes can evaporate.
Right, or is it Casimir energy, that you can take two plates, put them really, really close together, and they will experience a repulsive force between them because these virtual particles are appearing in between them and pushing the plates apart, as I understand. Do a search for that Casimir force, and you'll sort of go down a whole rabbit hole about that.
Star Trek uses that one periodically.
Oh, do they?
Yeah.
Hey, Star Wars! In like 4 days.
Yes, I don't have tickets yet. I'm a horrible human being. I meant to buy them yesterday, but I got sidetracked by eating awesome food.
Okay. Steve Chisel says, so trying to estimate a photon's lifespan is like trying to divide by 0. Yeah.
Yes, that's exactly what it is.
Yeah.
Don't divide the universe by 0.
So Steve Chisel says, so virtual particles are like imaginary numbers. So no, they're not. They're real. You could catch them.
Imaginary particles are real. Imaginary numbers are real too. They just are weird.
I agree with you. Michael Joven says, by the time you read this, it will be the future. So true. Paul Nash said, boom indeed, I can't wrinkle my forehead anymore. That's what we do here at Astronomy Cast.
Yes.
Steve Chisel says, the correct answer to Star Wars or Star Trek is Doctor Who?
Yes, I like that answer.
Okay. So has anybody... Oh my god!
What?
Oh, this person's name. You're going to love this. Okay, so this comes from OBGYN Kenobi. I have seen a couple of articles lately about quantum entanglement possibly being related to gravity. Is this a possible line of reasoning towards quantum gravity?
I don't know. Full stop. No idea.
Send in your articles, and we'll take a look. And I would love for us to do a show on quantum gravity. So
you don't like me, do you?
I would love to send you to the library for a few weeks to understand quantum gravity to the level that we could do a show on it. Is all I'm saying is what I would like. Maybe we'll bring in another ringer.
Yes.
We'll sequester. We'll get say Sean Carroll or I don't know Stephen Hawking or someone, and we'll have them join us. And then we'll talk about quantum gravity.
We could probably get Matthew Francis to come on.
Yeah. Or maybe Paul Sutter could take another crack at it, if that's his bag. Yeah, cool. Well, we'll do that. All right.
Checking the Twitterverse. So there's been strong aurora the past few days, and the meteor shower And David LPF points out clear and cold beats cloudy and rainy for meteor viewing.
Agreed. Michael Tobin says, I have to walk away now because it sounds like you're talking about God. Nope.
No.
Nope. Nothing about God.
Neither positive nor negative.
Nope. We're talking. I mean, the answer. What you're hearing is, I don't know. Just said
we're a
about,
God-neutral show.
Yeah. Exactly. We balance out. Yeah. So I mean, the bottom line is we don't know. We don't know. We don't know. We don't know. We don't know.
It's all right to not know.
Yeah. It's fine.
This is why we have scientists.
Steve Chisel says, did the now confirmed discovery of the Higgs boson actually disprove string theory? I don't think so.
Not yet.
No, string theory is tenacious. It won't take disproving very easily. Okay, great. So OBGYN Kenobi put in the focus on entanglement and quantum gravity. That's awesome. Thank you very much. We won't be able to digest it very quickly. So let's see. I mean, Matt Woods asks, in the flat universe model, how evenly is matter? Oh, sorry, how exactly is matter distributed evenly?
Say that again.
Okay, so in the flat universe model, how exactly is matter distributed evenly?
It has to do with the size of the box you look at. If you look at a small box, it's not distributed equally. If you look at a large enough box, it's distributed fairly easily. And flat universe has more to do with how much mass density you have. If the mass density is too high, the universe collapses. If the mass density is too low, the universe expands. We're ever in a curving way that causes it's just different geometries, and it comes down to, given enough time, do two parallel lines stay parallel, or do they converge or spread apart? Right.
Okay, well, I think we've reached the end of our hour. You've got to, well, welcome to Pacific time now. So you're going to be up late, but you can, and then you got to prepare, and you got a whole bunch of conferencing tomorrow, right?
Right. So for any of you who are in the San Francisco Bay Area and are hearing this live, because I will have left here by the time you hear this in the recording, I'm here for the American Geophysical Union Conference. I'm giving a talk at Pixar University tomorrow, and then giving a talk Friday at AGU. But most of the week, I'm probably going to be camped out in the poster hall, and I will tweet my location because I have some job openings coming up. They aren't posted yet, but we're working on the postings. And I'm interested in talking to people who might be interested in working for CosmoQuest. We have a couple of postdoc positions, a data scientist position, and a curriculum designer position.
Awesome. Yeah, that's right. This is what happens when you get funding, is you get to hire people as opposed to apologize why you can't hire people.
Exactly. And once we've hired, especially we're hiring a full-time administrative assistant. I have never been more excited about something before because, oh my God, I'm not to be trusted with certain things that I can just ask an admin to do that should be basic but require me to interact with physical reality, which apparently I kind of suck at. So that's going to be our first hire, is an admin, and that will really help getting a lot of just simple, small stuff like our newsletters going again and stuff like that.
I look forward to this hyper-organized Pamela. This is going to be great. All right, well, thanks everyone for joining us at this funny time. We appreciate your patience with our collective crazy travel schedule. This is the last episode then until the new year,
after Christmas.
Right? Yeah.
I don't know. Do you want to do one between Christmas and New Year? We can talk offline.
Yeah, we'll talk about that later. I mean, the Space Hangout, Christmas is on a Friday and then New Year's is on a Friday, so we're not going to do the weekly Space Hangout. The last weekly Space Hangout will be on Friday, and then we're going to take a break for 2 weeks for sure. So, but yeah, I can do a stream. Yes, I can record anytime. Anytime.
Cool. Right. Can I have this view forever? Can you find a way to fund me to just stay in this
Green screen,
this hotel room?
Yeah. No problem. So thanks everybody for joining us this week. We really appreciate it. Thanks, Pamela, for taking time out of your busy conference schedule, and we will see you all whenever this happens next.
And buy shirts at astrogear.spreadshirt.com.
Done. All right. Thanks, everyone.
Bye-bye.